Hey everyone, welcome back to Physics 11. So in this video we're going to be looking at Kirchhoff's laws. So Kirchhoff was a German physicist, Gustav Kirchhoff. So he studied circuits and how the voltages and the currents change depending on what type of circuit you set up. So let's take a look. Now we already know that we have two types of circuits that we looked at. So we looked at circuit in series and a circuit in parallel. So the manner in which you attach the components or the elements of a circuit can greatly affect the nature of the circuit, in particular its resistance. And there are a number of laws that we must use called Kirchhoff's laws. So again, when we talk about resistance, we're talking about the resistors that we have in our circuit. Now, the resistors don't always have to be just a resistor. So that can be another circuit element because no matter what you connect, could be a load, everything has its own resistance. So even though we simplified to just resistors, you could be working on some Arduino project and instead of a resistor, you're connecting a whole separate board or chip which will have its resistance. So just keep that in mind. It's not just going to be resistors all the time. Sometimes you're going to see in the question it says load, so that refers to the resistor as well, because no matter what you connect, no matter what kind of component you connect, each component will have some internal resistance. So let's take a look at the current law. So if you have a circuit that is in series, that means that one resistor is after another. That means that for the current to flow, there's only one path. So it has to go through each resistor until it comes back to its starting position. Right? So for example, if this is my total current that starts here, my I total, as it goes through resistor 1, right? There's only one way for this to go. This is resistor 2, resistor 3. The current only has one way to push through all of these resistors. So in that case, all the currents, if this is going to be your I1, this is going to be your I2, and this here is going to be your I3, all the currents are going to be the same because there's only one path. It does not split anywhere along the path. Now, what about circuits in parallel? Well, if you have a circuit in parallel, in that case, you have three different options for the current to split. So it may be easier to see this if you just take this diagram that I have here, which is kind of a normal way to represent circuits or elements in parallel here, but you can sketch it a little bit differently so you can see easier how the current is actually splitting here. So in this case, you can think of it like this, that you can have three resistors like this. So as you can see here, it's a lot easier to see it this way. We have this node here that goes like that. So for example, if I have my I total here, my I total, once it gets to this node right here, it has to split three ways, right? So this is my R1, R2, R3. So then the current will split into three different paths. So it'll go this way. This is going to be my I1. It'll go this way. It's going to be my I2. And it'll go this way. It's going to be my I3. So it's not as easy to see on this diagram, but all of this is just one single node because it's just one wire here. So that's the same as this node here. Same thing on the bottom here. This is just one single wire, so it corresponds to this node here. So when you have circuits in parallel, the current will take different paths, and as it splits, at some point it has to reconnect again. Otherwise, it's not going to flow if there's no connection, if there's no circular path for it to flow through. So in that case, all the currents are going to add up to the total current. So if I have my three resistors, I'm going to have three different current values going through each one, and then once they reconnect, they should add up to the total current. Now, when you do the math, sometimes because of rounding, especially like sig figs, you might have slight discrepancies on your values when you're trying to check that it adds up to the total, but just keep that in mind. It should be fairly close to your initial total current. So again, for series circuits, the currents are all the same because there's only one path. For parallel circuits, the currents will add up to the total current that you start. So Kirchhoff's laws, current laws, again, state that the sum of currents entering a junction or a node must equal to the sum of charges leaving the junction. So that's what I was just trying to describe in the previous slide. So this must be true, or else there would be electrons building up at one point in our circuit, which is impossible because of their strong repulsion. So you cannot have electron, sitting stagnant in some part of the circuit because they're all negatively charged. So they won't be just sitting in one place. So that's impossible. And if there is no way for them to go, they're not going to go there at all, right? So think of it like as a water. Same thing with water. If there is nowhere for the water to flow, it's not going to flow. It's just going to stay stagnant. But for electrons, it's a little different because they're also very repulsive. So they will push each other apart because they're all negatively charged. Now, what about the voltage loss? So we mentioned current. So let's talk about voltage. So this is our potential difference. So for the voltage law, the sum of the potential differences in the circuit must add up to zero. In a way, this is simply restating the law of conservation of energy. So any changes in energy, so if you remember we did this, our delta EK has to equal to, let's say, negative change in delta E potential, right? So when you put them all on one side, all the differences, all the deltas have to add to zero, right? So if you move this to the other side, you end up with that. So that's what I mean here by this. So same thing for the electric potentials, so potential differences. So our deltas. So difference means our deltas, right? So same thing here. Same laws apply, same conservation of energy. So let's see what the laws are for voltage. So again, remember there is an increase in potential across the terminals of a battery. So that's going to be your highest potential difference just across the battery if you measure the voltage in a battery. And there is a decrease in potential across any load. So any resistors do you have? So loads here means any resistors. In our case, we're representing everything with resistors. But again, this could be a whole appliance that you connect to your circuit. So whenever you have any sort of load, the voltage will drop as that load uses up some of that energy. So essentially, these increases and drops must add up to zero. So again, all the changes that you have, all the voltages still have to add up to the total. And again, because of the rounding, when you checking your work, sometimes you might have slight discrepancies, might be off by a few decimals or hundredths. So again, just keep that in mind when you're actually doing the math. Sometimes you might have some discrepancy just because of rounding, because of sig figs. So let's take a look at the, this is a circuit in series, and now we're going to talk about voltage. Now, there's only one path for the current to go through, so our voltage, our potential differences means that through each resistor, the voltage is going to decrease. So each load, each resistor here, so this is our R1, R2, R3. So let's say if you start with like 12 volt here, every time you go through a load, your resistance, your voltage will drop a little bit, right? So depending on the resistor, I don't know how much it's going to drop, but it will drop a little bit. So for example, if you only have two resistors in series, we call that a voltage divider because that's one of the simplest way we can actually drop the voltage for our purpose. For example, maybe you're working on some Arduino project where you need like the common voltages for that is like 5 volts and 3.3 volts. So maybe you want to have, you want to step down from maybe 9 volts to 5 volts or from 5 volts to 3 volts for whatever circuit that you need to connect to your project, right? So you can use a voltage divider, which is basically just two resistors in series, which allows you to reduce the voltage. So at this point would be your voltage would be lower depending on your R1 and R2. So if you have, I should make a note here, if you have two resistors in series, we call this a voltage divider. Okay, so that's just a term that you might hear in some either textbook or notes, or maybe you're looking up something on internet. So if you see voltage divider, that just means you have two resistors in series, which allows you to drop the voltage to whatever you need. Now in this case, we don't have two, we have three, but the purpose of this diagram is to show that the voltage is going to decrease with each resistor. So at the end though, when you add all the voltages, all the drops across each of the loads, they should all add to the total voltage that you start with. So you should still adapt to 12 volts that you started with. So that's, again, the law for circuits in series. Now, what about circuits in parallel? So in this case, if you start with, let's say you start with 12 volts here, right? So like a car battery, the voltage drop is going to be the same across each load, in this case, across each resistor. The reason is, again, because you can redraw this like so. So if you think of it this way, just like I did with the current, you can redraw this diagram like this. So that means that if you connect your voltmeter at the battery, so let's say you put your leads at the battery, right? And you measure your voltage here, it's gonna be 12 volt. You're gonna see that. But if you look at your diagram now, you can see that all of this is just one single wire. So it doesn't matter where you stick your voltmeter when you have your resistors in parallel, because you're still gonna end up with readings from basically these two nodes, which is gonna be exactly the same as that one, because this is all just one single wire. There's nothing really, any other loads in between them. So you're still gonna get your 12 volts reading. So that's why it's convenient to connect things in parallel, because you get the same potential for all of the elements that you have in your circuit. So for example, if you want to power up a light bulb and the light bulb requires 12 volt, if you have more than one light bulb, you want to connect it in parallel. Also, if one burns out, that doesn't prevent the other ones from keep working. So again, there's advantages and reasons for using each type of circuit, parallel or in series. This is one of the reasons, for example, we use circuits in parallel when we wire up our house light fixtures. We connect them in parallel so that when one light bulb burns out, it doesn't affect the function of other light bulbs, right? Because, for example, if the light bulbs were in series, then if one burns out, it basically stops everything else. But anyway, if you have a circuit in parallel, your voltages are going to be all the same. So your V total is going to be the same as your V1, V2, and V3 across the R1, R2, and R3. Now let's talk about resistance. Now there is no loss for resistance. There is no Kirchhoff's loss for resistance. But the total resistance in a series circuit is going to be the sum of all the resistors. And that kind of makes sense. The more resistors you add, the higher the resistance should be. Since each electron must push its way through each resistor, it should make sense that the resistance are cumulative. So in this case, we have the R total equal to R1 plus R2 plus R3 and so on. So you can keep adding as many resistors as you want. Now for a parallel circuit, as you add resistors in parallel, the total resistance actually decreases. Now we haven't talked about this earlier, but that's the case. And what happens with parallel circuits is that you're actually adding the reciprocals of each of the resistors. So in this case, if the electrons are forced through one path, then there will be much more friction than if there were multiple paths to choose from. Right? So if you have one path, they have to go through one path. There's no choice. But if you have multiple paths, now the electrons have more places to go through, so the resistance is going to drop. So think of it like, So for this middle point here, think of it like maybe you have a leak in a garden hose, right? So normally you have one nozzle that the water goes through. So you have high pressure. So the water jets out from the end of the hose. But if you have a bunch of leaks along the way, so you're adding more options for the water to escape, the water drops, right? So that's why electrons, same thing here. Electrons have more options for other paths to go through, so the resistance drops as well. So again, this is true even if the additional pathways are of high resistance. So it doesn't matter whether, for example, the leak in the garden hose is small or large, there's still going to be some loss of water. So same thing with the electrons. And in this case, we're actually going to be adding the reciprocals. Now, this is probably out of all of the laws and formulas you're going to see, this is probably the trickiest one because we have to deal with reciprocals. We can't just add the resistors like we did in series. So for parallel circuits, we need to do 1 over R. And as you can see here, it's not even R total equals to all this, it's 1 over R total equals to all this. So that makes the math a little complicated. If you try to define your R total, you have to deal with reciprocals, and then as a final step, reciprocate your answer, or you can cross multiply to get your R total. So let's summarize what we talked about so far. So if you have circuits in series, for voltages, all your voltages have to adapt to the total voltage. So you have your V total equal to your V1 plus your V2 plus your V3 and so on. So you can have more than 3 loads, so you can have more than 3 voltages. For the current, if you have a circuit in series, your current is going to be all the same because there's only one path for electrons to go through. So your I1 is going to equal to your I total, and it's going to equal to your I2 and to your I3 and so on. For resistance, we just mentioned resistance. If you have a circuit in series, the resistors add up. So your R total is going to equal to the sum of R1, R2, R3, and so on. So that's for circuits in series. Now for circuits in parallel, if you're talking about voltages, the voltage is going to be all the same. So your V total is going to equal to your V1, V2, and V3. So all the voltages are equal. When it comes to current, because now you have multiple paths for the electrons to flow through, you're going to have the currents add up. So you have your I total equal to I1 plus I2 plus I3 plus etc. And the most, I guess, confusing one is the resistance in parallel circuits, because now you have to deal with the reciprocals. So 1 over R total is going to equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. So that's the only, I guess, tricky one that we need to deal with. The rest is just either they're the same or you just have to add them. So that's the summary for circuits in series and parallel. So let's take a look at some examples here. So here's the first example. It says, what are the values for I1, I2, and I3 in the circuit shown? Now in this case, we have a circuit that's in series. So we're given all of the resistors, so we can find our total resistance. So we can find our RT, because in this case, it's going to be just R1 plus R2 plus R3. Now we don't know current I1, that's what we're trying to find. We don't know the current I3, that's also missing. But we know that the currents are going to be all the same if you have a circuit that's in series. So again, if you go back to your table here, for current we have I total equal to I1 equal to I2 equal to I3. So we're going to write that down as well. So I total equal to I1 equal to I2 equal to I3. So as long as we find the I total, we can know what the I1 and I3 is going to be. What else we need to know here? We're given the total voltage, right? We know the total voltage is V total is given, is 12 volts. So given the information that we have, this is unknown. We have all of these guys, so we can find our total. From here, we can find the I total as well, because if you use Ohm's law, which states that our V, in this case, we're talking about the total voltage, is going to equal to I total times R total, right? So we can find our R total. That's no problem. We just add all of the three resistors together, and we know this already, so we can find our I value from here. So I total is going to equal the V over R. Well, the V is already given, and the R total is just going to be the sum of all of these. So we can rewrite it as, again, V total over R1 plus R2 plus R3. Plug in the values for all of this, and here we have 12 volts for the voltage. R1 is 3 ohm, so 3.0 plus R2, which is 4.0 plus 2.0. So our I total is going to equal to 12 over 7 plus 2 is 9. So we get 12 over 9. So 12 divided by 9 is going to be 1.3 repeating. And this is amps. So there you go. We found our I total, and because of this, we can now say I1, I2, and I3 are going to be exactly the same because of the fact that the elements are connected in series. So we can just say that I1 equal to I2 equal to I3 equal to the I total that we just found, which is 1.3 amps. So that'd be the first example. As you can see, we used Ohm's law and we use Kirchhoff's law to state that the currents are going to be the same. So again, this right here is Ohm's law. Okay, and this right here, this is our it's got two H's. Kirchhoff's law for current, right? So we use both of them whenever you analyze circuits, and you can have much more complicated circuits than this. But the goal is to always kind of break it into parts, see whatever you have in series. You can add all the resistors to just have one resistor because you just add them together, and then you deal with the parallel parts. So whenever you're analyzing more complex circuits, the first thing you want to do is add any resistors that are in series. And again, make sure you read through the textbook. They have more examples that you can look at and get an idea how to analyze these more efficiently. So let's take a look at one more example. So in this case, we have a circuit that is in parallel. So for circuits in parallel, let's state the rules. So for the voltage, it's going to be all the same for circuits in parallel. So that means that we have three resistors. We're going to have three voltages, V1 equal to V2 equal to V3. Now for the currents, I total, we're going to have to add all the currents. We have three resistors, so we have three ways for the current to split. So we're going to have our I1 plus I2 plus I3. And for the actual resistors, we're going to have the reciprocal. So that's the only tricky part here. So 1 over R total is going to be 1 over R1 plus 1 over R2 plus 1 over R3. Now, these are all the laws that we need to know, all the rules that we need to know for this type of circuit. Now, let's see what we can do with this. The question says, what is the value for R2? So right here. Now, we know the total voltage, which is going to be the same for all of them. And we also know some of the resistors here already. So what we can do is, if you look here, we have R1 value and we have the V1 value. So let's write Ohm's law for this. So Ohm's law states that the V1 is going to equal to I1 times R1. Now we know the V1 and the R1 values, so we can find I1. And once you know your I1, then you can do the same thing for the resistor 3 and find the I3, and then you can find this one and that one, you know the total current. So this is your I total here, 1.80 amp. So after that, after you know your I1 and I3, you can then find your I2 from Kirchhoff's law. And then from here, you can find your R2 that's missing. So as you can see, we're using both laws all the time, either Ohm's law or Kirchhoff's laws. So let's find the I1 current. So I1 current from here, we can say that I1 is going to equal V1 over R1. Now we know the voltage 1 is going to be the same as the total voltage, which is 24 volt, over R1, which is 40 ohm. So 24 divided by 4, that's going to be 0.6. 40.6. And this is current, so this is amps. And we can do the same thing for V3. So again, we can say that I3 is going to be V3 over R3 here. So we're going to get 24 over 60, which is going to be 0.4 amps. Okay, so now we know our I1 and I3. We can now go back to our Kirchhoff's law and find our I2. So from here we can say that I2 is going to equal the I total minus I1 minus I3, right? So now we know these values, we can plug them in. I total is 1.8 minus I1, which is 0.6 minus 0.4. And we'll just see, what is that equal to? 1.8 minus 0.6 minus 0.4 equals 2.8. That means that I3 is 0.8 amps, right? So they all add to 1.8 because that's what they have to do. And now we can find our last part, which is find the R2 value. Well, we know again from Ohm's law that V1 equal to, or sorry, it should be 2 here, I2 times R2. Now in this case, we already know the current I2, we know the voltage 2, we need to find the R value. So R2 is gonna equal to V2 over I2, which in this case, again, the V2 is the same, so it's gonna be 24 volt, and I2 we just found to be 0.8. Sorry, that's not right. What is 24 divided by 0.8? That's gonna be 30. I was off by a factor of 100 here. So that's going to be 30 ohm. So that's the resistor value for R2. So as you work through the practice questions, again, I would suggest you first go through the textbook. You can read both of the textbook that we have, and look through the examples, look at their tips on how to solve circuits, how to analyze circuits. And again, whenever you have stuff that's in series, add those up first, all the resistors in series, find whatever the current, the voltage drop across those elements in series, and then deal with the ones that are in parallel. So if you have any questions, make sure you post them in comments on Teams.